When you look at a highly engineered neuroprosthetic limb, the mechanical complexity is obvious. But the true engineering challenge lies at the interface, right where the biological nervous system meets the synthetic hardware. Translating human intent into robotic action faces a severe physical bottleneck. The human body and exogenous electronics suffer from a profound mechanical mismatch at the tissue-electrode boundary. Compounding this is a software bottleneck. The nervous system does not transmit singular, clean instructions. It fires chaotic, multivariant nerve signals, making it exceedingly difficult to extract a distinct, actionable command. Overcoming these twin barriers requires a symbiotic architecture that solves both the physical tissue rejection and the algorithmic data extraction simultaneously. Sustained, high-resolution brain-machine interfacing relies entirely on pairing flexible, tissue-mimicking biomaterials with unsupervised topological clustering algorithms. A common misconception in neurotechnology is that a sufficiently advanced signal processing algorithm can compensate for a poor physical connection. In chronic in vivo applications, those algorithms consistently fail. Algorithmic success is strictly downstream of biomaterial compatibility. An algorithm cannot process data that a sensor fails to clearly record. Therefore, engineering at the material layer is an absolute prerequisite. Only after the biological interface is secured can self-organizing maps successfully translate biology into action. The peripheral nervous system exists in a soft, dynamic, and fluid mechanical environment. It pulses, shifts, and stretches with every physical movement. Introducing a traditional, rigid, exogenous electrode into this environment creates immediate friction. Physiological micromovements cause mechanical shear as the rigid implant scrapes against soft tissue. The body responds with an immune reaction, forming a thick glial scar barrier encapsulating the device. As this scar thickens, electrical impedance spikes and the signal-to-noise ratio plummets, rendering the hardware useless. To eliminate this shear, material scientists engineer biomaterials that emulate the structure and mechanical behavior of the brain's extracellular matrix. This requires a layered approach. Bioinert materials, like titanium, establish structurally stable frameworks for the electrode without triggering aggressive immune responses. Bioactive materials, such as bioactive glass, are engineered to actively encourage cell adhesion, promoting safe tissue integration rather than rejection. Meanwhile, conductive polymers like graphene and biocompatible coatings like PEG maintain high-fidelity signal transmission across the barrier. This leads to highly stretchable electronics designed to mimic human skin and organs. The substrate twists and bends, integrating seamlessly with biology. These flexible electronics offer a linear elastic response that precisely matches the mechanical properties of human tissue. When the tissue shifts, the sensor shifts with it, eliminating shear entirely. By matching the mechanics of the tissue, the hardware bypasses the foreign body response, securing the clean, long-term biopotentials required for robotic control. Acquiring a clean electrical signal solves only the hardware problem. The computational challenge begins immediately after recording. This chart displays a simulated peripheral nerve recording trace. It presents as raw, chaotic voltage data, a wall of dense biological static. Hidden within are distinct firing patterns. Each repeating spike represents a discrete motor neuron class, such as PD, LP, or PY cells, firing in sequence. A single sensor recording is actually a superimposed mixture of multiple neighboring axons firing all at once. The software must instantly isolate these individual axon classes from the mixture to assign specific prosthetic movements to specific neural intents. Untangling this multidimensional signal continuously, in real time, and without any manual human intervention, requires a highly specific mathematical approach. The cleanest hardware interface cannot function without a mathematical model capable of instantly separating true biological intent from surrounding neural crosstalk. To parse this data, engineers deploy a Cohonen self-organizing map, or SOM. This is a neural network designed specifically for unsupervised classification. An SOM functions by mapping high-dimensional raw signal vectors onto a simplified flat grid of artificial neurons. As data flows in, nodes dynamically adjust their weights. physically moving closer to similar signals to form distinct topological neighborhoods. In clinical settings, this creates a major roadblock. SOMs traditionally require an experienced human user to manually look at the grid and identify exactly where one cluster ends and another begins. To remove the human from the loop, researchers developed the CluSOT algorithm, a mathematical solution for entirely automated cluster boundary detection. CluSOT projects the SOM neurons onto a Cartesian grid, adding a z-axis for the hit frequency each receives. A 3D Gaussian surface function drapes over these nodes, spread by the distance between neighbors. Locating the local maxima reveals the centers of specific neural commands. The algorithm takes the derivative of this surface to calculate the steepest slopes descending from the peaks. A mathematical threshold, like g equals 0.7, acts as a strict cutoff. This draws rigid boundary lines, effectively fencing off the peaks to create separate, distinct zones. Through this process, the final separated clusters are derived automatically, requiring absolutely zero manual human interpretation. Each mathematically isolated cluster now reliably represents a discrete executable nerve command, ready for transmission to the robotic hardware. With the data cleanly clustered, the command signal moves out from the algorithm and back into the physical world. The translation pipeline concludes as the mechanical actuator receives the pulse and engages precisely with the original biological intent. This execution is entirely dependent on the dual solution: physical compliance at the tissue layer, paired perfectly with topological clustering at the data layer. The flexible biomaterial hardware ensures the biological host accepts the interface over a lifetime of use, and the automated SOM algorithm ensures the machine accurately parses and understands that host in real time. This bar chart projects the applications of brain-machine interfaces through 2030. Solving the chronic implantation bottleneck drastically increases the viable use cases, specifically driving the high projected impact in healthcare and neurorehabilitation. Mastering this symbiotic architecture moves neurotechnology out of highly controlled short-term laboratory settings and enables chronic, real-world biological integration. The future of human augmentation lies in the seamless, interdisciplinary merger of advanced material science and applied machine learning.